manipulate signals. All right, so I've said this idea of signals before. So how do I model some sort of a real world thing with math, right? That's the idea of what a signal is. I'm talking about signal manipulation. I gave the example the other day. A note of music is 440 hertz, which means it's a cosine, right, at 440 hertz. And there's all sorts of important signals that model real world things. We talked about this a little bit the other day, right? And we're going to talk a lot more beginning next week about this idea of additive combinations of sine and cosine, which is what we call Fourier series, okay? A unit step. So if I had a voltage source that was, let's say, 2 times u of t, that voltage source does not exist in the real world, right? That's a model for something. What's this modeling? What's that a model for? What's that? Well, an output of what? How could I physically construct something? So 2u of t means that the voltage that I see right there would jump up to 2 volts at t equal to 0, right? How would I physically construct that? What would I have to have? I'd have to have a source and a switch. So I'd have a 2-volt battery, right? Which I could get, right? And I'd have to have a switch that I close at t equal to 0. Those those two things are equivalent to each other. 2u of t is a model. There is no u of t source in the world, but the voltage I see at these terminals and the voltage I see at these terminals is the same. Okay, so it's a model for it. And then I talked the other day, I said if I have an extremely short burst, that's a pretty common thing, right? That's what I call a Dirac delta, right? So this guy was delta of t, right? That, a Dirac delta or an impulse. So a couple of things about this guy. What's the height of the Dirac delta here? What's the height of that thing? If I say he's got, if I put a 1 right there, what's his height? Yeah, basically is of an infinite height, right? So his height's the undefined technically, and what's his width? Infinitesimally thin, right? So it's basically 0. So what we say is this guy has an area from negative infinity to positive infinity. The area of that thing is equal to what? 1. The area under that is 1. All right, its height is in theory infinite. We said this kind of comes up if I did something like I took the derivative of u of t. So in other words, if I took the derivative of this guy here, what would that be? If you took the derivative of a unit step, what's the derivative before t equal to 0? 0. Derivative after 0 is 0. What is it right here at that point? Infinite. So we say it's the derivative of this guy is delta of t. All right. So that's the relationship between these two things. And that's a really important and crucial relationship. So we talked about that the other day. All right. So we got some stuff on the homework that you'll deal with respect to that one. All right. We can build up all kinds of models for real world stuff using that's why we study all this stuff, is we need models for real world stuff. All right. So there's a lot of signal manipulation that we run into. Again, this is the most boring thing in the world, really, to me. So I get time shifting, time reversal, time scaling, and adding and subtracting signals to make other signals. Okay. So we gotta understand those concepts. They're important, but not the most exciting stuff. So basically, when we talk signal manipulation, I got some signal f of t, and I transform it to some new signal g of t. All right. So f of t on the left here, this looks like u of t. And I'm trying to transform that into this g of t equal to f of t minus 1. So what I got to figure out is, what does it mean to go from f of t to f of t minus 1? Okay, that's what when we talk about signal manipulation, that's what we're talking about. How do I manipulate my base signal into something else? All right, so let's do that example here, right? Let's say I've got g of t equals u of t minus 1. Okay. So the way to think about this, I think we mentioned this briefly the other day, but if I have in general, this is called time shifting, and I write it like this: g of t equals f of t plus t naught. And if t naught's greater than 0, we move one way. If t naught's less than 0, we move the other way. So the way to always check to understand this is to basically go and look at values of t and see what the value of g is at those times, and see what the value of f is at those times, and you'll make sense of it. Okay. So let's look at it this way. If u of t at t equal to 0, u of t is supposed to jump up to 1, right? At t equal to 1, what's supposed to be the value of u of t? So here's u of t here, this graph. So u of t, so for t greater than or equal to 0, what's u of t always equal to? 1. All right, so at -1, what's it equal to? 0. All right. So if I want to figure out, if I said g of t equals u of t minus 1, now a lot of you guys probably already know, that means that I take u of t and move it which direction? To the right. Okay. But I can check that by plugging in the t value. So g at t equal to -1, I have g of -1 equals u of what? How do I check this? U of what? So we got to remember this relationship here, right? So what do I say? G of -1 is equal to u of what? -2. -2. All right. So what's that equal to? 0. Okay. Let me give myself some more. Oh, I can't do that. All right. At g of, so g of 0 is going to be u of what? U of -1. That's still equal to 0. At t equal to 0, I have g of, sorry, t equal to 1. I have g of 1, which is going to be u of 0, which is equal to 1, right? So what I see from that is that so I can always plug in those values. That's really helpful for me when I start giving you sort of weirder stuff, which is combinations of scales and shifts and all that kind of stuff. So I see that this guy gets shifted to the right by 1. So if t of 0 is greater than 0, then I shift. It's greater than 0, I shift left, which is a time advance. Oops. Which is an advance. Why do I call that an advance? Why do I call that an advance? If I shift it to the left, why is that an advance? Because it happens earlier, right? T equals -1 happens before t equal to 0, right? So if I shift something to the left, it's happening earlier in time, right? So if I have this guy, so a shift right is what I have, that would be a delay. Okay, it's happening later. Okay, not the most exciting thing. So but here's where it gets a little trickier, right? Let's say I have this function here. So I've got sine cubed of 2 pi 100t. All right, so that's my f of t. Now what I want to do is I want to compute g of t equal to f of t minus 0.003. So what do I do then? What do I do here? So it's negative, right? My shift is negative. So first of all, which direction am I going to go? I'm going to go to the right. How far to the right? 3 milliseconds, right? So am I going to take the whole thing and move it 3 milliseconds? I got to be careful. When we make these manipulations, what I do is I have to replace the argument of the function here. So is it going to be simply, so let's think of g of t equals f of t minus 0.003. Is that equal to sine cubed of 2 pi 100? How do I write that? Yeah, this could be a phase shift. How do I write this? How do I put the argument in here? I need to replace the t with t minus 0.003. So that means that this guy becomes t minus 0.003. Oops, too many threes. You're replacing the argument with this new argument, right? The argument of the function is t. I'm replacing that argument with t minus 0.003. If you don't do that, you'll end up with a completely different graph, right? In other words, I don't call this sine of 2 pi 100 t minus 0.003. I need to replace the t. I'm replacing the argument with this argument, right? That's the idea. Okay. So if I do that, this guy's going to shift to the right a little bit, and I would basically take this point and move it 0.003. Moving this 0.003 in time, that's correct, right? So this guy basically moves over 0.003. That is equivalent to what I have right here, right? This moves every point in that graph by 0.003. Okay, that's kind of the important point, especially as you get into some weirder stuff. So here you can see that shift, right? So this was the original f of t. This is the g of t, which is f of t minus 0.003. And I can see that where the zero crossing point was moved over to what appears to be 0.003. Okay. Again, not the most exciting thing in the world. All right. But the thing for me to always check is I can plug in and I can see the value of f of t at t equal to 0 now happens 0.003 seconds later. So I always want to plug in the value and see that it matches where it should have been in the original function. Okay. That's my way of typically checking this stuff. All right. So here I have a shift of positive 0.003. So that's going to move to the left, right? So basically the important thing is here is you always replace the time argument, right? In other words, you replace t with that value, right? Otherwise, you're going to get the wrong result, right? Now, what happens if I do a time reversal? So I have g of t equal to f of minus t. All right. What's going to happen? Well, I replace the time argument with minus t. Okay. So if I replace the time argument with minus t, what's going to happen? What's the graph going to look like? It's going to do what? It's going to flip which way? Well, so I'm going to plug in. So what I had here, this value right here is, I don't know, 0.0025, right? So if I plug in it's going to flip over the vertical axis, right? So basically this guy is going to move to negative 0.0025, right? So it mirrors everything across the y-axis, right? And I basically, because what I can check is that, so when I say g of negative 0.0025, that's equal to whatever f of 0.0025 was. All right, so it's a fairly straightforward thing to do. All right. All right. The other thing I can do is what I call time scaling. All right. In other words, where I multiply the time argument by some scaling factor. Okay. And that has the effect of either compacting the signal, in other words, making it tinier, or expanding it, making it wider. Okay. So let's look at an example here. So I have this function up here, f of t. This guy's my f of t. All right. And I said g of t is equal to f of 3t. Okay. So what I do again is I plug in the arguments and I do some checks. Okay. So let's see here. So just to be clear, this guy is a pulse that basically rises up at t equal to -1 and falls back down again at t equal to 1. Okay. So what I do is I plug in at different time values, I plug in what's going on. So at t equal to 2, g of 2 is equal to f of what? 6. What's f of 6 equal to? Well, let's go look at the picture. It looks like it should be 0. All right. G of 1 would be f of what? 3. Where's f of 3? Well, that's over here. Right? What's that? 0. I said g at t equal to 1/3. That would be f of what? 1. That's equal to what? 1. G of 0 is f of what? 0, which is 1. So if I plug in g of -1/3, that would be f of what? -1, which is what according to this? 1. This is exciting stuff, right? So g of -1, this is easy stuff though. It's maybe a nice break. F of what? -3. What's that according to this picture? 0. So what have I done to the signal here? What have I done by putting this scaling of 3 in there? What have I done? I've shrinked it. Yeah, I've compacted it, right? So basically what I'm seeing is, so here was -1. Basically this guy rises up, goes over, comes back down, where this is 1/3 and this is -1/3. So it's like that. All right. So by multiplying it by 3, I basically brought it in by a factor of 3. So in some ways, I think to some extent, this, when you look at these scalings, they look like to your brain, if you think of it like this, like it's doing the opposite of what you might think it's doing. I multiply by 3, so it's 1/3 smaller. All right. But the way I always do this is I always plug in numbers like that to do a check. All right. That's the best way to always do it. All right. So let's say I have g of t is f of 1/3 t. All right. So in this case, what would I do? Well, what I do is I plug in, I say t equal to 0. I have g, let's start at negative values. So t equal to -3. I have g of -3. That would be f of what? F of -1. So t equal to -3 is where this guy jumps up. Let's say I had -4, right? That would be g of -4 is f of what? -4/3. Where's -4/3? Well, that's over here. All right. That's equal to 0. This was equal to 1. So what am I doing in this case? What am I doing when I have the 1/3 t? So I have a number less than 1 here. I need to be careful. What am I doing? I'm expanding it. Yeah, so this guy's basically jumping up at 3 and going down at 3. Right? So I have expanded it. I got to be careful. If a is less than 1 or greater than 1, it's a compaction. Okay? Greater than 1, it's a compaction. Less than 1, and it's an expansion. Okay? All right. So again, not the most exciting stuff, but we need to know how to do it. All right. Now, let's look at this guy. This is where we get into modeling. So I got a pulse going on here, right? So this pulse jumps up to 1, and then it jumps down at t equal to 3. All right. I can say that this is a combination of unit step functions. Okay. So how could I say, so what 2 unit step functions would I have here? So let's see. Let's look at this. So u of t, what does u of t look like? Well, u of t is 0, then it jumps up, and then it's flat. What can I add to u of t to make it look like this picture? How do I get those 2 aligned? if I, yeah, so if I added to this guy, let's say if I added that, right? So basically we're saying this function on top plus this function on the bottom would give me this, right? So what I'm saying is basically from t equals 0 to t equal to 3, I have 1. And then from that point onward, I have 1 minus 1 or 0, right? So I could say that this function here, if I call this guy P of t equals u of t minus u of t minus 1, all right? Or minus 3, sorry. Minus 3, okay? That combination of signals leads me to this. All right, so the sort of thing that you have in the homework is making those combinations and all that kind of stuff.